Shock waves in traffic streams. The fundamental diagram of traffic flow for two adjacent sections of a highway with different capacities or maximum flows. This figure describes the phenomenon of backups and queuing on a highway due to a sudden reduction of the capacity of the highway, known as a bottleneck condition. So, when such condition exists and the normal flow and density on the highway are relatively large, the speeds of the vehicles will have to be reduced while passing the bottleneck. The point at which the speed reduction takes place can be approximately noted by the turning on of the brake lights of the vehicles. An observer will see that this point moves upstream as traffic continues to approach the vicinity of the bottleneck, indicating an upstream movement of the point at which flow and density change. This phenomenon is usually referred to as a shock wave in the traffic stream. The phenomenon also exists when the capacity suddenly increases, but in this case, the speeds of the vehicles tend to increase as the vehicles pass the section of the road where the capacity increases. So, types of shock waves. Several types of shock waves can be formed depending on the traffic conditions that lead to their formation. These include frontal stationary, backward forming, backward recovery, rear stationary, and forward recovery shock waves. So, frontal stationary are formed when the capacity suddenly reduces to zero at an approach or set of lanes having the red indication at a signalized intersection or when a highway is completely closed because of a serious incident. In this case, a frontal stationary shockwave is formed at the stop lane of the approach or lanes that have a red signal indication. This type occurs at a location where the capacity is reduced to zero, for example, at a signalized intersection. The red signal indicates that traffic on the approach or set of lanes cannot move across the intersection, which implies that the capacity is temporarily reduced to zero, resulting in the formation of a frontal stationary shock wave. So next is the backward forming. Backward forming are formed when the capacity is reduced below the demand flow rate, resulting in the formation of a queue upstream of the bottleneck. The shock waves moves upstream with its location at any time, including the end of the queue at that time. This may occur at the approach of a signalized intersection when the signal indicated is red, or at a location of a highway where the number of lanes is reduced. Next is the backward recovery, or formed when the demand flow rate becomes less than the capacity of the bottleneck or the restriction causing the capacity reduction at the bottleneck is removed. So, but for example, when the signals at an approach or set of lanes on a signalized intersection change from red to green, the traffic flow restriction is removed, and traffic on that approach or set of lanes is free to move across the intersection, causing a backward recovery shock wave. The intersection of the backward forming shock wave and the backward recovery shock wave indicates the end of the queue shown as point T. So next is the rear stationary and forward recovery shock waves are formed when demand flow rate upstream of a bottleneck is first higher than the capacity of the bottleneck, and then the demand flow rate reduces to the capacity of the bottleneck. For example, consider a four-lane or one-direction highway that leads to a two-lane tunnel in an urban area. During the off-peak period, when the demand capacity is less than the tunnel capacity, no shockwave is formed. However, when the demand capacity becomes higher than the tunnel capacity during the peak hour, a backward forming shockwave is formed. This shockwave continues to move upstream of the bottleneck as long as the demand flow is higher than the tunnel capacity. However, as the end of the peak period approaches, the demand flow rate tends to decrease until it is the same as the tunnel capacity. At this point, a rear stationary shockwave is formed until the demand flow becomes less than the tunnel capacity, resulting in the formation of a forward recovery shockwave. So we have here the figure 6.9, which is the shockwave at signalized intersection. Next is shockwaves due to a bottleneck. So, velocity of shockwaves. Let us consider two different densities of traffic, K sub 1 and K sub 2, along a straight highway as shown in figure 6.11, where K sub 1 is greater than K sub 2. Let us also assume that these densities are separated by the line W, representing the shock wave moving at a speed u sub W. If the line W moves in the direction of the arrow, that is, in the direction of the traffic law, u sub W is positive, with u sub 1 equal to the space mean speed of vehicles in the area with density k sub 1, or section P. The speed of the vehicle in this area relative to line W is u sub R1 is equal to u sub 1 minus u sub W. The number of vehicles crossing line W from area P during a time period T is n sub 1 is equal to sub ur sub 1 k sub 1 plus times T. Similarly, the speed of vehicles in the area with density k sub 2 in section Q relative to line W is u sub R2 is equal to u sub 2 minus u sub W. Since the net change is 0, that is n sub 1 is equal to n sub 2, and u sub 1 minus u sub W times k sub 1 is equal to u sub 2 minus u sub W times k sub 2. We have u sub 2 times k sub 2 minus u sub 1 times k sub 1 is equal to u sub W times k sub 2 minus k sub 1. So if the flow rates in sections P and Q are Q sub 1 and Q sub 2 respectively, then Q sub 1 is equal to K sub 1 times U sub 1, and Q sub 2 is equal to K sub 2 times U sub 2. Substituting Q sub 1 and Q sub 2 for K sub 1 times U sub 1 and Q sub 2 times U sub 2, equation 6.32 gives Q sub 2 minus Q sub 1 is equal to U sub W times K sub 2 minus K sub 1. That is, U sub W is equal to Q sub 2 minus Q sub 1 over K sub 2 minus K sub 1, which is also the slope of the line CD shown in figure 6.8. This indicates that the velocity of the shock wave created by a sudden change of density from K sub 2 on traffic stream is the slope of the curve joining the points associated with K sub 1 and K sub 2 on the volume density curve for that traffic stream. So shock waves and Q lengths due to a red phase at a signalized intersection. So using the equation 6.33, we can determine expressions for the velocities of the different shock waves and the Q lengths. So this confirms that this wave is a stationary wave, where r is equal to the length of the red signal indication. So the maximum Q length in sub ST can be determined from figure 6.9, from where it can be seen. So we have here this, which gives this equation. So in our example 6.4, the Q length at a signalized intersection. The southbound approach of a signalized intersection carries a flow of 1,000 vehicles per hour at a velocity of 50 miles per hour. The duration of the red signal indication for this approach is 15 seconds. If the saturation flow is 2,000 vehicles per hour with a density of 75 vehicles, the jam density is 150 vehicles per mile. Determine the following: the length of the Q at the end of the red phase, the maximum Q length, the time it takes for the Q to dissipate after the end of the red indication. So we have here our solution. First is determine speed of backward forming shock wave in W sub 13 when signals turn to red. So we have negative 11.31 foot per second. Length of Q at end of red phase is equal to 15 times 11.31 is equal to 169.65 foot. So in letter B, determine speed of backward recovery wave velocity. So we have a total of negative 39.2 foot per second. And C, determine the maximum Q length. The maximum Q length is equal to 238.45 foot. Shock waves and Q lengths due to temporary speed reduction at a section of highway. So let us now consider the situation where the normal speed on a highway is temporarily reduced at a section of a highway where the flow is relatively high but lower than its capacity. So we have here an example for length of Q due to a speed reduction. So the volume at a section of a two-lane highway is 1,500 vehicles per hour in each direction, and the density is about 25 vehicles per mile. A large dump truck loaded with soil from an adjacent construction site joins the traffic stream and travels at a speed of 10 miles per hour for a length of 2.5 miles along the upgrade before turning off onto a dump site. Due to the relatively high flow in the opposite direction, it is impossible for any car to pass the truck. Vehicles just behind the truck therefore have to travel at the speed of the truck, which results in the formation of a platoon having a density of 100 vehicles per mile and a flow of 100 vehicles per hour. Determine how many vehicles will be in the platoon by the time the truck leaves the highway. So first we'll use the equation 6.33 to obtain the wave velocity. So we have U sub W is equal to Q sub 2 minus Q sub 1 over K sub 2 minus Q sub 1. So we have our Q sub 2 as 1,000 vehicles per hour and 1,500 vehicles per hour for Q sub 1, and our K sub 2 as 100 vehicles per mile and 25 as 25 vehicles per mile. So 1,000 minus 1,500 over 100 minus 25. So we have our U sub W is equal to negative 6.7 miles per hour. So knowing that the truck is traveling at 10 miles per hour, the speed of the vehicles in the platoon is also 10 miles per hour, and the shockwave is moving backward relative to the road at 6.7 miles per hour. So determine the growth rate of the platoon. So we have 10 minus negative 6.7, so we have 16.7 miles per hour. So to calculate the time spent by the truck on the highway, we have 2.5 over 10 is equal to 0.25 hours. To determine the length of the platoon by the time the truck leaves the highway, so we have 0.25 times 16.7 is equal to 4.2 miles. So next is we will use the density of 100 vehicles per mile to calculate the number of vehicles in the platoon. So we have 100 times 4.2 is equal to 420 vehicles. Sorry for my PowerPoint. So 6.3.5, we have special cases of shockwave propagation. So the shockwave phenomenon can also be explained by considering a continuous change of flow and density in the traffic stream. If the change in flow and the change in density are very small, we can write this equation. So when such a continuous change to volume occurs in a vehicular flow, a phenomenon similar to that of fluid flow exists, in which the waves created in the traffic stream transport the continuous changes of flow and density. The speed of these waves is dq over dk. So in Greenshield's model, we have here the equation. If the Greenshield's model fits the flow density relationship for a particular traffic stream, equation 6.33 can be used to determine the speed of a shock wave as this. So we also have here the density nearly equal, and there is only a small difference between K sub 1 and K sub 2. The stopping waves, the speed of the shock wave, which in this case is a stopping wave, can be obtained by and the starting waves Yeah. Those special cases of shockwave propagation. So the shockwave phenomenon can also be explained by considering a continuous change of flow and density in the traffic stream. If the change in flow and the change in density are very small, we can write these equations. So if the Greenshield's model fits the flow density relationship for a particular traffic stream, the equation 6.33 can be used to determine the speed of a shock wave as this formula. So, in density nearly equal, when there is only a small difference between k sub 1 and k sub 2. In stopping waves, so equation 6.46 can also be used to determine the velocity of the shock wave due to the change from green to red of a signal at an intersection approach if the Greenshield's model is applicable. During the green phase, the normalized density is in sub 1. When the traffic signal changes to red, the traffic at the stop line of the approach comes to a halt, which results in a density equal to the jam density. So the speed of the shock wave, which in this case is stopping wave, can be obtained by this equation. Next is the starting waves. At the instant when the signal again changes from red to green, so vehicles will then move forward at a speed of bore u sub s2, resulting in a density of this. So the speed of the shock wave, which in this case is a starting wave, and is obtained by this formula. The velocity of the shock wave is then obtained as this. So example 6.6, length of q due to a stopping shock wave. Studies have shown that the traffic flow on a single lane approach to a signalized intersection can be described by the Greenshield's model. If the jam density on the approach is 130 vehicle per mile, determine the velocity of the stopping wave when the approach signal changes to red. If the density on the approach is 45 vehicles per mile and the space mean speed is 40 miles per hour. At the end of the red interval, what length of the approach upstream from the stop line will vehicles be affected if the red interval is 35 seconds? So by using the Greenshield's model, we have 61.2 miles per hour, and in using the 6.47 for a stopping wave, we have our u sub w is equal to negative 21.2 miles per hour. And since u sub w is negative, the wave moves upstream. Next is determine the approach length that will be affected in 35 seconds. So we have 21.2 miles per hour times 1.47 times 35 seconds is equal to 1090.70 foot. Gap and gap acceptance. So thus far, we have been considering the theory of traffic flow as it relates to the flow of vehicles in a single stream. Another important aspect of traffic flow is the interaction of vehicles as they join, leave, or cross a traffic stream. Examples of this include ramp vehicles merging onto an expressway stream, freeway vehicles leaving the freeway onto frontage roads, and the changing of lanes by vehicles on a multi-lane highway. So, the most important factor a driver considers in making any one of these maneuvers is the availability of a gap between two vehicles that, in the driver's judgment, is adequate for him or her to complete the maneuver. The evaluation of available gaps and the decision to carry out a specific maneuver within a particular gap are inherent in the concept of gap acceptance. So we have the following are the important measures that involve the concept of gap acceptance. So first is merging. It is the process by which a vehicle in one traffic stream joins another traffic stream moving in the same direction, such as ramp vehicle joining a freeway stream. So next is diverging. It is the process by which a vehicle in a traffic stream leaves that traffic stream, such as a vehicle leaving the outside lane of an expressway. Third is waving. It is the process by which a vehicle first merges into a stream of traffic, obliquely crosses that stream, and then merges into a second stream moving in the same direction. So, for example, the maneuver required for a ramp vehicle to join the far side stream of flow on an expressway. 4 is the gap. It is the headway in a major stream, which is evaluated by a vehicle driver in a minor stream who wishes to merge into the major stream. It is expressed either in units of time or time gap, or in units of distance, which is space gap. So next is time lag. It is the difference between the time a vehicle that merges into a main traffic stream reaches a point on the highway in the area of merge and the time a vehicle in the mainstream reaches the same point. And lastly, the space lag. It is the difference at an instant of time between the distance a merging vehicle is away from a reference point in the area of merge and the distance a vehicle in the mainstream is away from the same point. A driver who intends to merge must first evaluate the gaps that become available to determine which gap, if any, is large enough to accept the vehicle, in his or her opinion. In accepting that gap, the driver feels that he or she will be able to complete the merging maneuver and safely join the mainstream within the length of the gap. This phenomenon is generally referred to as gap acceptance. It is of importance when engineers are considering the delay of vehicles on minor roads wishing to join a major road traffic stream at unsignalized intersections, and also the delay of ramp vehicles wishing to join expressways. It can also be used in timing the release of vehicles at an acceptable gap in arriving at the freeway shoulder lane is maximum. So, to use the phenomenon of gap acceptance in evaluating delays, waiting times, queue lengths, and so forth at unsignalized intersections and at on ramps, the average minimum gap length that will be accepted by drivers should be determined first. So several definitions have been given to this critical value. Greenshields refer to it as the acceptable average minimum time gap and define it as the gap accepted by 50% of the drivers. The concept of critical gap was used by Raff, who defined it as the gap for which the number of accepted gaps shorter than it is equal to the number of rejected gaps longer than it. So the data in table 6.2 are used to demonstrate the determination of the critical gap using Raff's definition. Either a graphical or an algebraic method can be used. In using the graphical method, two cumulative distribution curves are drawn as shown in this figure 6.14. So one relates gap length t with the number of accepted gaps less than t, and the other relates t with the number of rejected gaps greater than t. The intersection of these two curves gives the value of t for the critical gap. So in using the algebraic method, it is necessary to first identify the gap lengths between where the critical gap lies. So assuming that the curves are linear between t sub 1 and t sub 2, the point of intersection of these two lines represents the critical gap. The t sub c is equal to t sub 1 So 6.4.1 Stochastic approach to gap and gap acceptance problems. So the use of gap acceptance to determine the delay of vehicles in minor streams wishing to merge onto major streams requires a knowledge of the frequency of arrivals of gaps that are at least equal to the critical gap. This in turn depends on the distribution of arrivals of mainstream vehicles at the area of merge. It is generally accepted that for light to medium traffic flow on a highway, the arrival of vehicles is randomly distributed. It is therefore important that the probabilistic approach to the subject be discussed. It is usually assumed that for light to medium traffic, the distribution is Poisson, although assumptions of gamma and exponential distributions have also been made. So assuming that the distribution of mainstream arrival is Poisson, then the probability of x arrivals in any interval of time t second can be obtained from the expression of this, where p of x is the probability of x vehicles arriving in time t seconds, and mu is the average number of vehicles arriving in time t. So if v represents the total number of vehicles arriving in time t seconds, then the average number of vehicles arriving per second is lambda is equal to v over t, and mu is equal to lambda times t. We can therefore write equation 6.50 as p of x is equal to lambda times t to the power of x and e to the power of lambda times t over x prime. So substituting 0 for x will therefore give a probability of a gap h is greater than or equal to t occurring that this. So it can be seen that t can take all values from 0 to infinity, which therefore makes the two equations a continuous functions. The probability function described by first equation is known as the exponential distribution. So it can be used to determine the expected number of acceptable gaps that will occur at an unsignalized intersection or at the merging area of an expressway on ramp during a period t. If the Poisson distribution is assumed for the mainstream flow and the volume V is also known, let us assume that t is equal to 1 hour and that V is the volume in vehicle per hour on the mainstream flow. Since V minus 1 gaps occur between V successive vehicles in a stream of vehicles, then the expected number of gaps greater or equal to T is given as this. Frequency is equal to V minus 1 times E to the power of negative lambda times T. And the expected number of gaps less than T is given as the frequency H less than T is equal to V minus 1 times 1 minus E to the power of negative lambda times T. So we have here from example 6.7, number of acceptable gaps for vehicles of an expressway ramp. So the peak hour volume of an expressway at the vicinity of the merging area of an on-ramp was determined to be 1,800 vehicle per hour. If it is assumed that the arrival of expressway vehicles can be described by a Poisson distribution, and the critical gap for merging vehicles is 3.5 seconds, determine the expected number of acceptable gaps for ramps vehicles that will occur on the expressway during the peak hour. So we have here first is to list the data. We have V is equal to 1,800 vehicles per hour and T is equal to 3,600 seconds and lambda is equal to 1,800 over 3,600, which is V over T is equal to 0.5 vehicles per second. So calculate the expected number of acceptable gaps in 1 hour using the equation 6.54. So we have the frequency H is greater than or equal to T is equal to 1,800 minus 1 times E to the power of negative 0.5 times 3.5. So it is equal to 1,799 times E to the power of negative 1.75 or 312. The expected number of occurrences of different gaps T for the various previous example have been calculated and are shown to this table 6.3. The number of different lengths of gaps occurring during a period of 1 hour for V is equal to 1,800 vehicles per hour and an assumed distribution of Poisson for arrivals. So the basic assumption made in this analysis is the arrival of mainstream vehicles can be described by a Poisson distribution. This assumption is reasonable for light to medium traffic but may not be acceptable for conditions by heavy traffic. Analysis of the occurrence of different gap sizes when traffic volume is heavy have shown that the main discrepancies occur at gaps of short lengths that is less than 1 second. The reason for this is that although theoretically there are definite probabilities for the occurrence of gaps between 0 and 1 seconds, in reality these gaps very rarely occur, since a driver will tend to keep a safe distance between his or her vehicle and the vehicle immediately in front. One alternative used to deal with this situation is to restrict the range of headways by introducing a minimum gap. So the equations 6.54 and 6.55 can then be written as these two formulas, where t is the minimum headway introduced. So example 6.8, number of acceptable gaps within a restrictive range for vehicles on an expressway ramp. So repeat example 6.7, using a minimum gap in the expressway traffic stream of 1 second and the data. We have V is equal to 1,800, T is equal to 3,600, lambda is equal to 0.5 vehicles per second, and we have here now the T is equal to 3.5 seconds. So to calculate the expected number of acceptable gaps in 1 hour, we have H is greater than or equal to T is equal to 1,800 minus 1 times e to the power of 0.5 times 3.5 minus 1.0 is equal to 1,799 times e to the power of negative 0.5 times 2.5. So we have 515 expected number of acceptable gaps in 1 hour.